Welcome you all to the second half of the first honor session. It's a James K. Mitchell lecture. My name is Chung-Gi Chung from Seoul National University. First of all, it is great honor and privilege to chair this session. Mitchell lecture is managed by TC102, ground characterization from in situ tests. So I will introduce Professor Antonio Fonseca. Now, I will take over microphone to Professor Fonseca, and he will briefly introduce this lecture.
Thank you, Mr. Chair, and Professor Antonio James for the word. So we are here presenting the 8th James K. Mitchell lecture, which was launched some years ago. Our colleague John Power from Geolabs UK will be lecturing on this title, In Situ Testing, Ensuring Quality in Equipment Operation and Interpretation. Can we do that? It's an interesting title and comes really very converging some of the preoccupations and the challenge that Dr. Peter Day gave us in the beginning of this session. So the first James K. Mitchell lecture was performed and initiated in Porto in the second international conference in 2004. It was in situ soil testing from mechanics interpretation, and it was presented by Professor ICU, one of the former students from James Mitchell in US. Please. And at that time, the author cited Dr. Mitchell saying that the ability to treat results of cone penetration and pressure meter tests in sand and clay on a realistic theoretical basis enhances very well their value for site characterization determination of relevant soils mechanic properties. Please go on. So I have a series of the James K. Mitchell lectures. So the second lecture was Undisturbed Sand Strengths on Seismic Cone Tests from Professor Paul Main. He is here. The third one, please, another one. The third lecture was in 2008 in Brazil, Geoenvironmental Site Characterization from Dicta Campanella. The fourth one, sorry for that, I was expecting to have a point here. Can we proceed? The fourth lecture, the CPT in offshore soils investigation, was presented by Dr. Tom Loom in US, CPT 10 in 2010. Next one, please. The fifth lecture, Interpretation of In Situ Tests, Some Insights from Professor Peter Robertson. He's here also in Brazil. And following, there is a mistake there, following six, it was in Las Vegas. Mike Jamelkowski, Professor Jamelkowski is here. He talked about role of in situ tests in geotechnical characterizations of copper tailings. Finally, before this one, please, the seventh one was recently, last year, in Gold Coast, in our site characterization of silty sand soils, tricky materials to characterize in situ as in lab, as most of us know. So, John Powell is here already. Sorry for delaying your presentation. The education is here resumed. Please, next one. The career is past most of his career in the BRE in UK, responsible for research and consultancy, and really doing a great work on in situ testing. And now he is technical director of Geolabs. Please. So he was core member of our TC since a long time ago, since the 90s, and he led most of our activities. We owe him a lot. Finally, I will not end citing this magnificent book. It's co-authoring with Peter Robertson and Tom Lund. Cone penetration testing in geotechnical practice is still the Bible of these CPT tests. So thank you, John, for accepting this invitation, and we look forward to your lecture. Thank you so much.
And While they're bringing my slides up, can I thank TC 102 for giving me this honour for the 8th James K. Mitchell Lecture, and also the organising committee of this conference for giving me the opportunity to give you a brief insight into the paper. So, this 8th J.K. Mitchell Lecture, In Situ Testing and Ensuring Quality in Equipment, Operation and Interpretation. And I'm saying, can we? I'm going to give you a brief insight into some of the questions I would like to address with that. And it may be slightly odd for me to put up a slide here about sampling coming from a laboratory as well as in situ testing. But it's not unknown for people to make up samples on site, and therefore sampling and laboratory testing got something of a bad reputation in the past. So, why do we do in situ tests? Well, it offers many attractions over sampling and laboratory testing and the problems of sample disturbance, etc. And in situ tests are undertaken in place. You know, we've either pushed or drilled a hole and got a device into there, which we then load in some way, while actually taking records of what is happening during that test. We would say that the advantages of in situ tests are speed. Generally, a lot of them are a lot quicker than we can do any laboratory testing or sampling. We can get a lot more data out, and that's an important thing. And we can almost get continuous data out down a profile. And also quality. When undertaken correctly, the quality of in situ testing can be very high indeed, and better than some of the problems we have with routine sampling and laboratory testing. And I'd say we hope, because obviously there are problems with in situ testing as there are with laboratory and sampling. So I would just like to highlight those points: quality and when undertaken correctly, because those are the big points that I would like to discuss over the next few minutes. Hopefully most of you, and I know you come from very, very different backgrounds in the geotechnical fraternity, but have come across the basic range of in situ tests. The SPT that we've heard already mentioned today, and some people say the best thing we could do with the SPT is throw it away, but it's still widely used, so let's see what we can do with that. The cone penetration test, one of those widely used in situ tests. The Marchetti dilatometer, which we'll hear more about, that is growing in popularity. Pressure meter tests, putting rubber bags into the ground and expanding them laterally. And also the vein test, which has been used for so long. Those are probably some of the classical tests, but there's a lot more. And we could probably extend that slide even further to incorporate all in situ tests. And you've probably all seen these sorts of charts, originally set up by Peter Roth, looking at the applicability of in situ tests for giving us geotechnical parameters. And you'll see on that slide, there's quite a lot of A's. A's are that it's highly applicable. And even B's are moderately applicable. So we've got some very, very powerful tools in situ tests to give us the geotechnical parameters that we want for our designs. And it's probably even better than that if we were up to date. To update that slide, I think there'd be a few more A's in there now. So, the problem with in situ testing is quite often you see in the literature some wonderful success stories, how well in situ tests have gone and given parameters. But then again, we all tend to only publish our successes, don't we? We very seldom publish our failures. And we often find that some of the successes that we read about in the literature, when we try and use those correlations elsewhere on different soil types, or even on the same soil, they don't seem to work. So why is this? Well, it could be the quality of the data that was originally used in developing the correlations, or the quality of the data that has been gathered and is being used with that correlation now. This whole thing of rubbish in, rubbish out, if we have rubbish test results, then there's no point in trying to interpret them into geotechnical parameters. But if we have good test results from our in situ tests, we can still get rubbish out if we're using inappropriate correlations. And what we're trying to achieve is quality data in from our in situ tests and quality interpretation out, so we have confidence in the geotechnical parameters that we are gathering. So we need to consider the data quality, and that can be affected by equipment, manufacture, consistency of manufacture. Equipment, maintenance. It's one thing to manufacture good equipment, but maintaining it is crucially important, and calibrating it is very important. And then operation. Is it then used correctly? All trying to give us confidence in what we're trying to get out. And only after we have real confidence in the data that we have can we possibly have confidence in the interpretation methods that we use to get our geotechnical parameters. The first of those points of quality of data is really controlled by our testing standards and adherence to them. These are the important points. In many cases, the standards that we use have evolved from country to country. You know, they're purportedly working to the same test, but we have little variations in each country. To just use a classic example there for simplicity, taking a laboratory test, the Casagrande test for liquid limit. We all were using the Casagrande cup, but the Americans were using the American base, the British were using the British base, the French, the Germans, etc., and all getting different results. So it's not surprising that we then have problems when we try and use correlations from one country to another, because we're not actually correlating together the same information. Now in Europe, we've heard the Eurocode mentioned already today, but in Europe we are developing a set of standards for in situ testing. And these are being adopted as ISO standards as well. So they're going to have far wider impact than just within Europe. So from now on, we should all be producing, or a lot of us producing, data, test results to the same standards, to a common basis. And I say hopefully, because I would love to do a survey to know how many people in this room are actually using the new standards. Testing standards contain a set of requirements for manufacturing the equipment. I'm going through this because it shows you where, if we work to these things, everything should be wonderful. They set the requirements for the equipment calibration and maintenance, what shall be done. They tell us how the test will be performed, what shall be done. And they set out how the test result will be obtained. And they also set out, quite often, very detailed reporting requirements. These detailed reporting requirements are sufficient to allow us to check the data quality of the results we have got. So that's why these testing standards are so important. And there's the list of in situ tests, the standards that exist now or will come out this year, and all that list, bar one, will be with us by the end of 2017, I think. Some were produced way back in 2005, but it's taken time to produce some of the others. So did you know about these? I hope you did. Some examples of standards and why maybe some of the changes to the standards are so important to us. We've heard about the SPT test already today. It's used worldwide, driving a split spoon sampler into the ground for given distances with a free-falling weight. And then we get a blow count for the number of blows to penetrate. But we often see results like that. Wide scatter. Those are 4 different investigations. Any one investigation has got a decent profile, but they don't compare to each other. And one of the main reasons for this is likely to be the delivered energy from the SPT hammer. Now, one of the things the new standard says is that we have to look into the energy ratio, the ratio of the delivered energy from a hammer to the theoretical energy it should give. And it says this has to be known if we're going to make any sort of interpretation into geotechnical parameters from the data. Also, a certificate of calibration shall be available. Now, I'm quoting some of these things because I know the UK is not perfect in this and we're trying to drive it in the UK to have these things. But I wonder what's happening elsewhere in the world. That was a set of results. Each of those points is the energy ratio for individual hammers calibrated once the new standard came in the UK. And you can see we've got a range of energy ratios from 43% to 89%. So is it surprising that we can get different N values when different people work on the site? But at least if we know what the energy ratio is, we can apply a correction to our results and maybe then form a common basis for our N60 results. Also, that is what we'd like to see from a calibration of an SPT hammer, a tight grouping, 10 successive blows. It won't be exactly the same every time, but that's pretty close. And we'd be quite happy that has an energy ratio of about 77%. That's not what we want to see, where we get erratic blows from a hammer, probably because it's worn. The one thing the standard doesn't tell us, though, is what is the rejection criteria. So it tells us we have to do this calibration, but doesn't say when we should be throwing hammers out and saying that's a useless hammer to be used. So measuring energy ratio is a step forward, but there's a lot more needed to be done with the SPT to make it the reliable test. Showing you some examples now of what the standard for dynamic probing has come up with. And you should all know this because the standard's been around for 12 years, but it's a series of configurations from light to super heavy, changing the size of the cones, changing the weights that are being used to drive the cone into the ground. The same as the SPT, we are taking a blow count for a given distance. But the DPM has changed in its configuration. Did people know that? If you use the new configuration, then previous correlations will be invalid. We have to be aware of that. Also, torque has to be measured now in the standard at intervals down the profile. An energy transfer assessment, the same as with the SPT, is desirable, but doesn't have to be done. It also suggests that maybe we should be starting to think more about unit point resistance, RD, and dynamic point resistance, QD, to allow for better correlations. I'm not going to show you the equations for that, we haven't got time, but just to show you what that means, here we've got a profile with a light DP, a medium DP, and a heavy DP, the N10, the blow counts, and you can see 3 different profiles. If we reprocess these into RD, you can see that things are starting to come together. And if we use QD, it doesn't matter what configuration we use, we still get a similar result. So surely QD is a far better way forward for correlation purposes in the future. And here's a very simple correlation between the cone resistance, QT, and QD. So this is a potential, a way forward for better interpretation of dynamic probing. It's a way forward. Shall we do away with N10L, N10M, and that should say N10H, not M. So we're quickly moving through different in situ tests. And I mentioned the pressure meter test before, inflating a rubber bag laterally in the ground. 3 types of pressure meter. One where we form a hole, drop the pressure meter bag into it and expand it. One where we self-bore the probe into the ground with hardly any disturbance, hopefully. And one where we push the probe into the ground and then expand it laterally. 3 very different types of pressure meters. Standards for these are available or becoming available. They all just report a pressure volume expansion curve, a corrected one. That's as far as the test result goes. Note I keep referring to test results because the testing standards don't give you geotechnical parameters. They only give you a test result. The interpretation comes at a later stage. But the standard for the Maynard pressure meter, one of the pre-board pressure meters, also requires you to present the Maynard limit pressure and the Maynard modulus EM. Straightforward it should be, it always has been. But there's a pressure volume expansion curve. We have the pressure along the bottom axis, the volume up the side. The Maynard limit pressure, it's when we double the volume of the probe. Easy. The Maynard achimodulus is simply the slope of the linear portion, the straight portion of the pressure volume curve. We can all do it, easy. But this is a series of interpretations done by a group of people of the same pressure meter test results to give the Maynard limit pressure. Big range of values. Why? Because they're all not doing it by hand. They're trying to curve fit and put it into software and get the software to give them the results. Something's going wrong. A simple interpretation procedure being made more complicated and more variable. And the same thing happens with the Maynard modulus. We're going backwards here. We're trying to be too clever. On a positive note, though, here are a series of limit pressure results from pressure meters, from the cone pressure meter, the full displacement, the self-boring pressure meter, the Maynard pressure meter, but not the Maynard limit pressure, the infinite volume limit pressure. And I think you'd agree, we'd be pretty happy that all three types of devices there are giving us the same limit pressures when interpreted in similar ways. This is something that's very useful for using testbed sites for, of course, in trying to do these comparisons and gaining confidence in our in situ tests. So I'd now like to briefly talk about the CPT. We all know, hopefully, that one of the problems with the CPT is the pore pressures that are generated in clays affect actually the measured parameters, particularly the cone resistance. And we have to correct for that by using a factor called A, which is the ratio of the shaft diameter, as you can see here, to the diameter of the cone, the area, the cross-sectional area of the shaft, the cross-sectional area of the cone, which can be done geometrically. But the standard says you shall do it by calibration in a calibration chamber. Why? Well, the problem is that if you produce 1,000 cones the same, geometrically they'll all have the same area ratio. But when you calibrate them, here's an example from 115 identical cones. The range was from 0.72 to 0.88. That's a significant range in my mind. The O-ring seals and the dirt seals were the main factors affecting this and giving those around, but those are the real values for that cone. So in soft clays, that could have an error in the cone resistance, the corrected cone resistance of 10 to 12%. I'd say that is significant, but some people say that's insignificant. I don't see how it can be, especially as it can be allowed for, and therefore it should be. Excuse me. And the effect of that, you can see a series of cone profiles here, which are pretty good, pretty close. Not all the same cone, two different cones. But by using the correct A-valve values, I think you'd say that's pretty impressive, the agreement we then get in the corrected cone resistance. So it is worthwhile doing what the standard says you shall do. Yes. I thought we'd taken these out, but this must be from that other memory stick as well. I shall talk about some problems with friction sleeves. This is a calibration for the load cell for a friction sleeve from a cone, and you can see it's far from linear. This was only found because people were getting zero readings at very low loads. So a modification had to be done to this cone, and when the modification was done, that's the calibration that it then achieved. And what that meant was you moved from the cone, the friction sleeve results on the left-hand side of the profile here, which in one case was 0 down to 8 meters, and the other case was very low, to that very close fitting group on the right-hand side. So we still have developments to do in equipment to ensure that we're getting reliable results out. This is just an example now of the fact that water pressures can affect friction sleeve results as well. That's a series of cones, all tested on the same site, side by side. Very different friction sleeve results. Quite worrying, because if you turn those into other parameters, there's a big range of values. But we can apply some corrections to these. And that's when the first ones have been corrected for unequal end areas of the friction sleeve, which is now, this is in the past, that is actually no longer allowed now. Your friction sleeves have to have equal end areas. And if we apply full pore water pressure corrections, then we get even better correlation. There's some problems at the top end still, and we've still got some way to go on this, but we are improving our interpretation of friction sleeve results in soft soils. Relative sizes of cone and friction sleeves. Some work from Australia showed us that if we have slightly larger friction sleeves, and here they have made them 0.1 of a millimetre larger than the cone, 0.2 and 0.3, we get higher friction sleeve results. And that is worrying. And if it's right, then we have to look into this in more detail. Robertson, in about 2014, found similar things. But all these are within the allowable tolerances that are within the standards. Some of the cone manufacturers have designed their cones so that they are up to 0.3 of a millimetre larger in the friction sleeve diameter than the cone. Most of them have a maximum range of 0.1. And this is something that we're going to have to look into now to see if we can improve these friction sleeve results and get more consistency. We hadn't realised that this tolerance allowance was maybe too coarse in the past. So we have to rethink the standard. And also, these tolerances link into the whirring of cones as well, the worn friction sleeve result. I had a recent conversation with somebody on a site who had just bought a new CPT rig. And I was asking them how this was going. And they said, oh, this is great. We can push things in so fast. We'll really complete this work a lot quicker now. So I then said to him, but you're going to keep to the standard rate of testing? And he said, what standard rate? We have a problem here with training, I think, and education. We know that rate effects are a problem in all our testing, be it CPT, pressure meters, vanes, plates. So unless we can ensure consistency, we have to keep the rate the same so that we can keep that consistency. We need better training. Second conversation. Do you change the filter element on your cone every test? Oh, yes. Can I see some of your filters? Here's one. That seems rather small. So it's set back from the outside diameters of the cone. Oh, does it matter? Was the reply to me. And I shan't tell you what I said to that. Training again. You know, it's too easy to buy equipment and think that we can then go away and test. But we have to know what we're doing. You know, it's not just the engineers, the technicians, the people doing the operation have to know why they're doing it and why we need quality. So we can eliminate many potential errors and pitfalls by using good best practice, we've heard that mentioned today already, through testing standards and training. I hope I've convinced you about some of that. Please be convinced. I do hope so. The other aspect as well I'd like to briefly touch on is validation of actually new equipment. So people may build new equipment to the standard to fit everything else. But how do we know it's going to give us the same results as similar equipment? Here's an example for a cone pressure meter, a newly developed cone pressure meter. Now I go back to one of the testbed sites, and here we have those limit pressures from a series of pressure meters, not just the cone pressure meter, but all of them. And those are the limit pressures that came out in this validation exercise. Quite consistent, but consistently high. And that was slightly worrying. What was wrong with it? And it was found that, in fact, that in the software package, where it was selecting the 0 for the volume and the pressure calculations, was wrong. Once that was corrected, we moved to the red triangles. So it wasn't a consistent offset, because you can see we're getting far closer sets of data there. It varied from profile to profile. It's still not back to the other results, but I would need more time to show you the other corrections that had to be done to bring it so that everything worked. But this is important that we validate actually fresh designs on equipment back to what we have already and we have confidence in. The final topic is, now we've got good quality data, let us consider getting some parameters. And we were fortunate a few years ago to run a project across Europe on 14 testbed sites, using the same devices across those sites. So we've eliminated one aspect of variability here, which is equipment. And so we have a chance to look at some of the data. And there's a lot more of this that will be in the paper. Let's think about the shear strength in clays from CPTU. A lot of the historical scatter is because of the mixing of corrected cone resistance, the thing I talked about for poor water pressure effects, and earlier correlations that didn't do that correction. Also, we use a database of shear strengths to do those correlations and establish them. And that may vary. It may be done on piston samples, it may be done on hammered samples, it may be different types of shear strength tests. These all have an effect on our correlations. And you will all have seen equations of that type. I've kept equations to the minimum here, so that's just showing you those. And we have to come up with these factors, NKT, N delta U, and NKE. And work has been done on that, and they've been well established. And here on one of the soft clay sites, you can see laboratory strengths from piston samples and the corresponding cone profiles based on NKT, N delta U, and NKE that were available at the time that this work was done. All agreed remarkably well. We were very confident in this. Then we started taking samples with block samplers, far better quality samples. And that made us have to have a rethink on our correlations, because what happened was the strengths from the lab with the block samples were up here. So lo and behold, we now have to have a new set of factors to correlate with the strength from the block samples. It can be done, but we have to say, have you got the confidence in using those higher strengths when you come to design? You need to know, this is really stressing the fact that you need to know what your correlations are based upon, the soil types, the lab testing types, and the sample quality. Another example of how somebody else came up with determining their NK factors. People often use 15, 17, but they range from 10 to 30 with validity. On a very large job, people had taken good quality samples and did laboratory testing, and then correlated their cone results back to their lab results, and then did a distribution. And in this particular case, they came up with an NK factor of 24 for this particularly stiff clay that they were working in. So that's another way. You can't just pluck an NK factor out. You have to have confidence by validation against other work. So we've seen this figure before, just to show you what other testing results can be shown on this plot. That is the shear strength determined from the Marchetti dilatometer. Very nice fit to the piston sample strength. When we use the pressure meter and do determinations of shear strength from the pressure meter, that matches very well with the block strength. What is appropriate? We have to think about this when we look at these different correlations and different determinations of shear strength. This is really a warning. We have to understand the test. We can also determine, this is to show you very briefly some work that's been going on, in determining horizontal stresses from the cone pressure meter. This is one of the hardest things for us to determine regularly, is horizontal stresses. And you can see here, I hope, that we got pretty consistent results from a number of sites between the interpreted horizontal stress and the best estimate, but all over reading. A few years ago, HiSweU came up with a correction of this type to correct the actually interpreted horizontal stress to reduce it. It's a CU-based correlation. And when we apply that type of correlation with certain little tweaks and modifications, you can see the remarkably good agreement we then get. So there's real promise there and a way forward, we hope. Some final examples. Shear modulus, we've heard that mentioned today. Very popular now using the seismic cone. The green dots here are downhole shear wave assessments for shear modulus, GVH, so it's the downhole. And hopefully you can see a yellow line on there. Yes, you can on there, it's not so clear on here, which is a site-specific correlation to that data. Looks very good indeed. Sorry, from QT to shear modulus. Now, lots of people have come up with correlations for cone resistance to shear modulus, and there's a few of them. Slightly alarming, the spread of results we get. This is again saying, take care. You know, you see a published correlation, it may well not work. If you did all these correlations and took the average, it might fit quite well if you look at that. But certainly individual ones are quite worrying in how far apart they can be. A second soft clay site, exactly the same type of thing, very good site-specific correlation I can derive to a particular equation type. And when we look at the correlations in the literature, it's falling down the middle again. Not always the case, because when we start looking at a stiff clay site, here we see the data is falling to the lower bound. We've got some overestimates of here of up to 3 and 4 times what the small strain shear modulus might be by using some of those correlations. Worrying, very worrying. Part of this may be linked to the fact that QT probably correlates best with the horizontal small strain shear modulus, the GHH. And that may be where we're going wrong here. We're trying to correlate something that doesn't easily correlate with the stiffnesses that we're looking at from downhole testing. Anisotropy of stiffness, something we need to look at and address. The other thing is that from the Marchetti dilatometer we get a stiffness, ED. Now, there's a plot of GHH, the horizontal stiffness in situ, to ED. And there, I think we would start to say that the stiffnesses we are determining from the Marchetti dilatometer are much closer related to the horizontal stiffness and not the vertical stiffness. And that needs to be taken into account when we're using these parameters for interpretation. I think one thing we do need to do is the other area we have within the pressure meter is that we can do unload-reload loops. And these unload-reload loops agree remarkably well between the different types of pressure meter. In the paper, you'll see this more clearly. But in this particular figure, you see the results from different types of pressure meters, the self-boring, the cone pressure meter, the triangles and squares, and also some data from small strain measurements from underplate transducer systems, large 1 meter diameter plates, and also from laboratory triaxial data. So here we're finding everything is coming together. It's very nice in this particular case because it happens to be a soil where K0 is very close to 1, and anisotropy is not such a problem for us. But that's very encouraging in trying to get our shear modulus decay curves, mixing pressure meters with laboratory measurements at the top end from resonant column. So, conclusions. Gathering of test results. A lot of the equipment that we have available for us is excellent. There's no doubt about that. There's a lot of very good people producing very good equipment. We're still improving equipment. I hope I've shown you that by the problems with some of the friction sleeves and things, and also fixing problems with existing equipment. We're putting together far better procedures for calibration, maintenance, operation, and reporting. And hopefully, with the full acceptance of standards and the correct training of those who are doing the testing, then we will get test results will be far more consistent between operators, devices, and around the world. Please don't forget that standards are for both contractors and consultants. Consultants have to know what's in the standards, particularly when they're specifying the tests. And more importantly, though, the contractors have to adhere to the standards and make sure they carry out the tests correctly. So we hope that with more consistent results, then we can get better interpretations of the geotechnical parameters, and that our correlations will improve with time. We must not oversimplify our interpretation of in situ test results. We need quality databases of information which can be used to validate and improve existing interpretations and develop new ones. We need to understand how the ground behaves when loaded by these different devices to better understand how to interpret them. And a balance between sophistication and oversimplification has to be maintained in all we do on the interpretation of in situ tests. General correlations that can be established have a validity in giving us an insight into the likely values of parameters. But local correlations, site-specific correlations with high-quality sampling and testing in the laboratory are crucial. In situ tests do not work in isolation. I would love to say they did. So finally, I hope that in some way I've begun to convince you that the answer to in situ testing, ensuring quality in equipment operation and interpretation, and the question, can we, is, wait for it, yes. But we have to work at it. Thank you very much indeed.